I'm a PhD student at WPI. My advisor is Brian Mitchum, and my area of research is performance-based design. So, in general, the performance-based design approach for fire protection design requires the definition of safety goals, objectives, and performance criteria. Okay. The selection of fire design scenarios upon which the trial designs are evaluated, the assessment of the consequence of the fire design scenarios using the fire effect tools, and also evacuation tools, which are selected according to the needed degree of analysis required for the performance-based design. Of course, input data are needed also in order to use these tools. So this presentation is focused on the selection of the tools for use in the PBD based on the applicability of to the building and the fire protection problem of concern, specifically for the fire effects tools. Parallel presentation could have been set up for evacuation tools or structural response tools for fire threats, but are not discussed here. As presented in the SFPE guidelines for substantiating fire models for given application, the fire effects tools can be categorized according to their level of complexity. We have algebraic models, zone models, and CFD models. And in this list, we added the hybrid tools, which can be two combined of these fire effect tools or fire effect tools with a ventilation network or evacuation tool. The SFPE guidelines emphasize on the technical applicability of fire effect tools to be used for a given application, but it should be noted that the use of the tools is also regulated by the time and the resources that the user have in order to use this to solve this problem. For example, for fire protection engineers dealing with a new project, at the beginning, in the feasibility or concern design, the level of details of the analysis is quite low, and the fire protection engineers is required just to give a very quick response to the fire problems. In that case, we can use algebraic equations if needed, and the calculation speed and the time for analysis is quite high. Going on with the scheme design, data become more available concerning the building contents, layout, and so on. So we can use more sophisticated tools such as zone models. In that case, the computation speed decrease, and also time of analysis decrease because we go on in the project. In the detailed design phase, all the details become available, so very sophisticated tools such as CFD can be used. And again, the computational speed decreases because it requires more time, and the time for analysis also decreases because we go on the project, and after detailed design phase, we go on the construction phase. In academia or research environments, the time for solving a particular problem is greater than for projects. So in that case, we can have like PhD research can be used, and one example presented in my paper it concerned a hybrid tool that has been designed for smoke extractors in tunnels. It's due of PhD research, and it its conclusion is to use a hybrid tool combining a CFD model for fire effects and ventilation network. The second example is what has been used by the Nuclear Regulatory Commission and dealing with the fire problem, the fire risk within their global probabilistic safety assessment of nuclear power plants. So they started, and in this quantitative risk assessment, all fuel source can be potentially a fire start. So the first question is how to get rid of the fire scenarios with no consequences on the safety of the nuclear power plant, because the fire would be too low or the safety targets are too far away from the fire. So what they did is that they designed a screening method based on algebraic models and conservative assumptions in order to get rid of these scenarios. After that, they still had to deal with thousands of fire scenarios. So what they did is that they used fire simulation batches for all the rooms that were not very complex in their geometry, like shoebox rooms. In that case, they can use zone model in order to get the analysis for these kind of fires. For more detailed fire scenarios requiring more detailed analysis, they used a 3D spatial representation for these scenarios, and of course they used CFD models. So based on this kind of studies in the literature, and if we go on with the NRC type of studies and the NUREG report 1934, we try to use that studies and combine it with the building environment specificities. So it's like, in that case, we have one type of facility, nuclear power plants, and we have like multiple building occupancy groups and diverse kind of system building occupants. For the NRC also, the systems have to be protected because of their final objective. In the built environment, we have to protect the occupants. So all these analyses led to the creation of what we called a testbed environment. So the testbed environment process is described on the left, as it is in the paper, in a very detailed way. But for this presentation, we can summarize or categorize this process in three phases. The pre-processing phase, which basically introduces the content of each possible study of interest and gathering building information. The performing and analyzing phase, which is the core of each study, linking the performance-based aspect of the study with the use of tools for a given application, and defining same scenarios for this analysis. And after that, the post-processing phase, in which the results of the two applications for different scenarios are compared. The ability of the used tools to address the PBD issue is also established, and guidelines related to the use of the tools for this issue, we hope, can be detailed. So the use of the test-based studies is to provide guidance to use appropriate tools for a given application within our PBD framework. They are not aimed to increase the validation domain of the tools. They are not aimed also to provide fire design scenarios to PBD application. This phase is another part of my PhD research. And also because of the scope of the test-based studies, we would like to have participation of the worldwide fire protection engineers, but also researchers and regulators, because our final product will be, we hope, guidelines. So in concrete terms, the test-bed studies will be organized as follows. So for the pre-processing phase, we will create a website in order to present each potential study case of interest and to collect the building configurations. Once the fire design scenarios are selected, each participant performs the analysis with their tools of their choice and upload the results of their analysis on the website, but also with a description how they use the tools. And after that, in the pre-processing phase, all the results are analyzed by the participants, but also all the stakeholders involved in our project, in order to conclude and potentially write the guidelines. So the ready-to-use building layouts concern the first phase, step 1 to 4 of the testbed process, or the pre-processing phase. And we would like to have the maximum of information regarding the building and its contents, the structure, its contents, the systems, and the occupants. And all this information is mainly collected from designer files. So the objective related to gather all this information is to, in that phase, we don't have the scenario, so we don't know which data we will have to gather to run the tools. So we would like to have all this information before, and also the level of detail that we have now concerning the use of tools may be different in the future with upgraded version of the tools, which would require more data, but also new tools that then can be used for PVD applications. So far we have been working on this phase, and we have been gathering some configurations, so we hope to have this ready on the website by the end of this year. So we like to distribute that on some kind of Google group, and we would like to create the additional input files for evacuation purposes, for example. And we already started to create the FDS files for these configurations. And within this Google group, we will have to get participation of fire protection engineers in order to implement the step 5 and 6. We are regarding the scenarios for use for this building configuration, and of course to help perform all these simulations. So one example that I gathered and start to build with FDS is related to a dormitory. So I found out a student room layout on the internet, and with Pyrosim, I built this layout, so describing the geometry but also the contents. And with Pyrosim, based on this configuration, I was able to recreate all the building. Of course, for a lot more complex geometry, such as an hospital, I had the help of a designer in order to recreate the patient room floor. So what's typically what we will have in the pre-processing phase, all this information. And in the subsequent phase, if we want to use FDS for our analysis, so we will have to look at the contents and the arrangement of a patient room, and once again using Pyrosim and the design find, we will have this configuration. So basically, we have all these layout for the patient room floor. Also, we are looked at design fuel packages. So in order to facilitate the implement of fire design scenarios. So basically, we'll look at information such as the heat release rate curves and smoke and fire effluents. So we started to create a database on experiments which could be used for any fire effect tools. And we also looked at created FDS packages for 3D simulations. So basically, we looked at a NIST experiment, so if the love seat combustion, and we looked at the difference between distributing the heat release rate on one surface or several areas in order to recreate the flame spread and the flame characteristics of this experiment. And we look at what influence it will have on the near-field analysis, looking at activation of heat and smoke detectors on the ceiling and ignition of secondary fuel items. Because all these analyses are highly dependent of the location and the flame characteristics. So we will look at time activation for one when the heat release rate is distributed in one area and several areas. So in the near field analysis, we can have like a difference. But because we are looking at this result within the overall engineering analysis, we will have to see if describing a very detailed fuel package has an influence of the overall analysis. Maybe it doesn't have. Also, we found that for the far-field analysis, the degree of detail in describing the fuel package wouldn't have been that high because we are looking at smoke transport, for example, out of the room of fire origin. So regarding the participation of the fire protection engineer, for example, in the pre-processing phase, it will help define priorities of the studies to conduct. It will help in the second phase to identify the goals, the objectives, and the scenarios, and also perform the analysis and share his knowledge. And in the last phase, he will get the benefits of the guidelines by improving their knowledge of the use of tools for a given application. So we have the same for the architects. So I would like to thank NIST for supporting this work, and to thank you for your attention. And if you are interested in participating, we can send me an email for further information. Thank you.
Does anyone have a question for Alberto? All right, well, let's move on to the next speaker then. Thank you very much again.